since we can plug in any angle into the sine and cosine functions, we can graph just the sine function or just the cosine function. Remember that the unit circle itself actually is graphing them with respect to each other, because an ordered pair value is something like a cosine of an angle comma a sine of an angle. So we're not seeing just one of them independently, we're seeing them combined together. If I looked at just one of them, though, we can plug anything into sine and we can get an output. So I could graph the sine function where the y values are the sine of the angle, and the angles themselves, or arc length, because in radians they're synonymous for a unit circle, are the x values. This is a picture of that would look like for the sine function. Okay, and the cosine function is below it. These functions are often referred to as periodic functions because they repeat the same pattern over and over, which we see on the unit circle when we go past 2 pi. We have those coterminal angles. The patterns repeat over and over there as well. Okay, so in the sine function, I'm going to highlight, like, there's one period in the negative set of x's, and there's one period here in the positive set of x's. So a period, we usually would highlight the first period of sine starting at 0 and going to 2 pi, because that's one complete circle, right? The circle goes from 0 to 2 pi. If you're going to go from the x-axis, positive x-axis, back to the positive x-axis, it's 0 to 2 pi. Okay? So looking further at this graph, the domain of sine of x is all real numbers because you can plug any angle into it. We already mentioned that before. So all real numbers in set notation, or negative infinity to infinity in interval notation. But the range, since it outputs a ratio, the highest x value that's ever achieved is 1, and the lowest x value that's ever achieved is -1. They are achieved, so you're going to have brackets on that range, -1 to 1, or if you want to write it in set notation, you could use inequalities. -1 is less than or equal to y is less than or equal to 1. I usually prefer the interval notation, probably for both of these, so I'll circle those. So we have our interval notation for our domain and for our range. Okay. What kind of symmetry does the graph of sine of x have? Ooh, we haven't talked about graphical symmetry in a little bit. It has the kind of symmetry where you go from quadrant 1 to quadrant 2. It's mirrored across the origin, so it is symmetric with respect to the origin. And that makes it an odd function. Remember how we defined if a function was symmetric with respect to the origin, it was odd. It's been a minute since we talked about that, but it is an odd function. Now let's look at the cosine function. So the cosine function, if I highlight again one period from 0 to 2 pi, this is going to be what the cycle looks like. It's similar to the sine cycle, it's just shifted. So if you pick sine up and shift it over by half a pi, you'll get the cosine curve. Remember, that is not a surprise because they were co-functions by, we said 90 degrees, but 90 degrees is pi halves, so we have that going on here. I also want to mention here, since I just mentioned degrees, we never graph these periodic functions in degrees because the axes would be stretched to 360, which is a ridiculous amount of x values to have to do. We always graph these in radians, so make sure that you're in radians. Okay, so those need to be in radians on the x-axis, I think I was saying. All right, and so I was talking about the cosine function. The domain of the cosine function is also, again, it inputs an angle, so it's also going to be all real numbers. So all real numbers, or the interval from negative infinity to infinity. And its range, since it's again a ratio, same pattern. Highs at +1, lows at -1. So it's -1 to 1, or again, -1 to 1, depending if you want to write it in interval notation or set notation, but we prefer interval. So I'll just circle my 2 intervals there for the domain and the range of cosine. What about symmetry? All right, so this one is symmetric with respect to, the same thing going on both sides of the y-axis. So it is, I'm going to write a different color, but it's symmetric with respect to the y-axis. So symmetric with respect to the y-axis. And this means that it is an even function. Odd functions with symmetric with respect to the origin, even functions with symmetric with respect to the y-axis. And recall that if it was symmetric with respect to the x-axis, it wasn't a function because it wouldn't pass the vertical line test. Okay. And the next page, our top, starts with a statement. Notice how both functions have regularly repeating minimum and maximum values. And we can talk about since they're regularly repeating, that is about the period. The period is the amount of time that it takes for them to repeat, time or distance. And so in a distance of 0 to 2 pi, whatever it happens to be, there's a peak to peak or valley to valley or middle to middle, but the period for both of these is 2 pi. That's how long it takes for them to repeat. And they also have amplitude. Amplitude for these is defined to be 1 because there's a distance of 1 from their center line. So if you take their average of their values, the middle line right there, it's 1 up, 1 down. Net being 2, of course, because you go up 1 and up down. Okay. Now, considering any real number s and its opposite negative s, these numbers correspond to arc lengths in the unit circle that are symmetric with respect to the x-axis. These arc lengths are our angles in radians. So again, we've talked about this in terms of degrees, but my angle s, my angle negative s just go in opposite directions on the unit circle, so they're going to line up across from each other, or they're going to line up from each other in symmetric with respect to the x-axis. And so their sine values of s and of negative s are going to be opposite of each other because the y values are negative. So this leads us to 2 very important identities. First is that sine of negative x is equal to the negative of sine x. That's also a property of odd functions, by the way. Remember, for odd functions, we would have said in an odd function, it's always true that f of negative x is equal to negative f of x. That's a property of odd functions that's true for sine of x here as well. Now, cosine, since the cosine relates to the sine, of course, related to the y values. That's why you have the positive and the negative. When you have the positive and negative, cosine relates to the x values, and so those are both going to be positive. So the identity is going to be cosine of negative x is equal to cosine of x. And again, our in general identity for those evens that we saw a long time ago is f of negative x is equal to f of x. So it's true for any even function, including cosine of x. Just as with sine and cosine, we can graph the remaining trigonometric functions. However, we want to consider their domains first. Take a look at the next page. Now, tangent, its domain is not going to be all real numbers because it was that ratio of x divided by y. The reason that sine and cosine you could do all real numbers is because you were dividing them by 1 every time, because you're dividing by the hypotenuse. So this one, for tangent, since it is y divided by x, can't allow the x value on the unit circle to be 0. And the x value on the unit circle is 0 at multiples of pi halves. So you see at those pi halves values, we have asymptotes on our tangent graph. This is what the graph of tangent would look like. Okay, so its domain, this one can't be written in interval notation very well. It needs to be written in set notation. but it's going to be the set of all x such that x is not equal to, and it's not every pi halves because pi is 2 pi halves, right? It's only the odd pi halves. So we can say this two different ways. We could say to make an odd number, you can take an even number, like 2 times anything is even, right? So 2k plus 1 becomes odd. So that's an odd number times pi halves. Or the other way you can say this is if you have pi halves, so x can't be pi halves is the first one, and then plus any k pi. So if you go from there and you add pi and you add pi, or you go back pi, because k can be positive or negative, you'll get all of them. It turns out that these two things are the same, because if you get a common denominator, note that pi halves plus 2k over pi over 2 does add back up to 2k pi plus pi over 2, and you can factor the pi out, so that's 2k plus 1 pi over 2. So just to show that those are two different ways of thinking about it, but they are exactly the same. So it doesn't matter which of those two you write, whether it's just odd pi over 2 or starting with pi over 2 and then a gap of pi size to get to the next one. Okay. Now, that takes care of the domain, and again, two different ways to write it. You can choose one of those. They're both in set notation. The range is the y values that we achieve. You can see from our graph, since our ratio can have very small things for x, it can get very large for y. So it's going to be infinite positive or infinite negative in the, not the y in this ratio for the unit circle, but the y in the outer of the function right here. So the range is going to go infinite. So the range is going to be negative infinity to infinity, or all real numbers in set notation. Okay. Now the period of sine and cosine was 2 pi, but the period for tangent, it repeats. If I highlight one of it repeats in a distance that is just pi wide, right? Pi halves to negative pi halves, just pi wide. So the period of tangent is just pi, not 2 pi. Okay, let's look at some of the other ones. I might make another video. This one's getting a little long.